Thank you very much for the. All right, so yeah, accept it. So Katia, really thank you for the invitation to give the seminar. I'm really happy to be able to talk here to the inverse problem community about this topic. So this is a joint work with Alberto. We started some years ago, and it's it's about data prediction in quantum mechanics, but looking at it by through an inverse problem. So I wonder now how many of you have thought, reading the title, maybe this is another guy taking the advantages of the data science wave. Now, I don't know if that's what you have thought, but I have honestly to confess that I would have thought about that, about another person trying to surf in this data science wave. But the honest truth about this is that this is not our case. Our situation is a bit different. So our situation is more about paper where we have been trying to accommodate some of these new ideas, new saying that people are always talking like in data science and in many other situations. For example, one of the questions that I wanted to understand, that's actually the main motivation of our work, is this that I have heard in several situations, several occasions. I have heard that if you have enough data, you can forget about physics and use data to still predict. So the idea is that if you have enough data, you can predict, forgetting the physics. The first time I heard that, it was like very shocking to me. That's like, what? I mean, are we like hundreds, centuries of science, of physics, they are now outdated? So I wanted to accommodate that in my way of thinking, and my way of thinking is through inverse problem. That's what I did my PhD, and that's the way I try to think about, right? So then when I started to think about that, I felt like I was just like walking a mountain, the mountain that I have always walked. But this time, I looked at the ground, and the ground was full of oranges. There were oranges all over the places, and that was shocking. Where is the tree? Where are these oranges coming from? And obviously, the answer of where these oranges are coming from, it could be easy if one find an orange tree, right? If you find an orange tree, the trick, the secret is completely revealed. You wouldn't know how the oranges would have dropped from the tree, but it's not any more surprising, right? It's not any more surprising, the idea that you find oranges on the ground, because there are these orange trees. Right, so the idea now, it will be basically that. So with Alberto, we have tried to find the orange tree. We are not interested in the fact of how you make prediction using data. The only thing we want to understand is that if you have enough data, it's not surprising anymore that you can predict without using the physics, or in another way, saying forgetting the physics. That's what I heard in many situations. So I'm going to talk about that. So the first thing I'm going to try to explain is what I mean by forgetting the physics and predicting only with data. So that would be the first, like set up the framework. Then the second part would be the oranges on the mountain. So that's actually, I mean, the fact that data determine the evolution. Then in the third part, I will talk about the orange tree. That's as the trick, it reveals that you don't see, I mean, like the reason why oranges are in the ground, even if you didn't know how they drop, but they are there. So that's actually our orange tree with Alberto and I, is the initial to final state inverse problem. And the final part will be just the map to the orange tree, or other way say, like how we solve the inverse problem. That's the way we use. Maybe there were other, but that's the way we used. Okay, so let's start about the forgetting the physics and predicting only with data. So probably you know that the motion of quantum particles are usually described by families of wave functions. There are functions that I describe like that. So this dot that I write here is basically that I'm forgetting the variable x. It's just that this is for every time I have a function, okay? Okay, now if the motion takes place under the influence of an electric potential, here the potential will be denoted by V, and will depend on time and variable x, then the wave function will satisfy a partial differential equation, this called the Schrödinger equation, that is described by E partial of t, the Laplacian, and here with the Hamiltonian is given by minus Laplacian t. So the usual way of predicting in PDEs is like, all right, we are given an initial state, and then the way we predict is basically solving the initial value problem, right? So we describe the UT, this will be, the UT will be the map that takes the initial state into the state at time t. And if we want to we do this through the whole interval of time, we will have the whole evolution. And that will be the classical way of making the evolution, right? This is what now people call phenomenology-driven prediction. What is the drawback of this type of phenomenology-driven prediction? Is that you require the knowledge of the Hamiltonian. The knowledge of the Hamiltonian means that you need to know the physics, right? You need to know what is the exact law. Because you need to know the exact law, that means that you need to know the exact V in order to make this classical prediction. So what these people, these scientists, data scientists or computational scientists were thinking, I don't know. I don't exactly know what they meant, but the only way that I could understand about forgetting the physics was the following way. So let's consider now the data-driven prediction problem, approximate problem, where we will have a number n, that it will be a number of samples, right? And we will define the initial to final state set with n elements in the following way. It will be d of n, and it will be the pairs given by the initial state and the final state. And that will happen for n samples, right? So in that sense, the data-driven approximate prediction problem will be given at time t in the interval 0 t, when it's possible to compute an approximate un at time t from the data that you have, so that this un is actually an approximation of the state that you are looking for when this n is going to infinity. That could be data-driven approximation prediction problem. Why this is data-driven? The data-driven reason is that the Hamiltonian, So in here, the Hamiltonian that I'm assuming is the one that I have already described. So I have assumed that the Hamiltonian has a particular structure that is given by the dynamic part and the potential part, right? So it's the minus Laplacian plus the V. But the full description of the potential V is ignored. It's something that I don't know. So in that sense, this is data-driven prediction, because I'm forgetting somehow the physics. I'm like ignoring something about the physics, not obviously the whole structure, but something about the physics. And then I'm trying to still make a prediction, right? So this is what, let me say again, this is what it means to me. Let's forget the physics and predict only with data. That's what the people were saying. Or that's let's say, let me say more like probably honestly, is that's what I understood. Okay. So now let's think about the data prediction problem more in general terms. This was an approximate because you are not given the exact form, right, of the problem. But since I'm a mathematician, I'm more about trying to understand why they can predict using data and forgetting the physics. I will make the problem a bit more like abstract, more general, probably more ideal from the practical point of view, but it will be useful for understanding what is going on. So I will be given a potential that this potential is, I'm considering here the simplest possible case of the potential in terms of integrability and boundiness in time and space. And then I'm going to consider initial data in L2. And this is something that we know from a long time ago, that there exists a unique solution that is in L2 for every time and is continuous with respect to time. So this is a solution for the initial value problem that we have considered earlier. So now we will consider the evolution map as just the map that takes the initial state F to the whole function U, not to any specific state, but the whole solution U, right? So it's something that it's depending on the two variables. This, as we know, is a linear, it's bounded. That's what I would call the evolution map, because it's what it encodes the whole evolution about the particles, right? So now when the time it takes the final time, where here is denoted by capital T, I will call this map, the UT, the one that I was describing in the previous in this slide here, the one that it takes the function to a state in time, that will be called the initial to final state map, right? Because it takes the initial state into the final state map. Okay. So now what is the data-driven prediction problem in this situation? This is the ideal case, right? But that's the one that we want for understanding data scientists. So the question is it possible to compute the UT, the U from UT? Is possible to compute the evolution map from the initial to final state map? And that again is the same spirit, right? This is, let's forget physics and let's predict only with data. And probably for many of you have already realized that the data set that I was considering before, this data, the initial to final state set, is nothing but endpoints given in the graph of the operator initial to final state, right? These endpoints, right? So that's why we were thinking on approximation. Now we have the full operator as data. And that's the reason why now we aim for more, and we aim for the whole evolution map, right? Okay. So now let's talk about the origins of the mountain. That thing that we found shocking, this thing that we found surprising, or at least I found surprising. So for that, to do that, we will see that this data determine the evolution map. So for doing that, at least in the situation that I need an a priori assumption on the type of potential V. So actually, I will need a super exponential decay. That's the type of decay you will see here. And probably many of you are already, like when you see this exponential like that, you are already guessing why this is happening, right? So why this V had to be, it's basically exponential, but exponential it has to be in two senses. One is in L infinity and the other is in L2, right? Okay, so now the theorem we have with Alberto is as follows. So let's take V1 and V2 to have super exponential, two potential that has super exponential decay for dimension greater or equal than 2. Then what we are able to see is that actually the equality of the initial to final state maps associated to the potential V1 and V2 imply that the whole evolution of the system is equal for the two different Hamiltonians, right? So the evolution is determined by the initial to final state map. All right. This, in principle, if you think a bit about that, is a non-trivial fact. And in order to put it in a very simple equation, let's do something that is formal, and at the formal level, it would be like that, right? So it could be, remember that every UT applied to a function f is just the state. And the state satisfy an equation that is the partial derivative of t and the Hamiltonian multiplied to that. Right. So let's forget about the initial data, and let's think in terms of the state map. So of the initial of the state map, of the one that takes the initial state to the state in time t. So this is like at the formal level, it satisfies an ODE, right? Which is this ODE that you wrote there. Where for the ODEs are different for each of these Hamiltonian, right? Because the Hamiltonian itself is different in principle. However, you are assuming that the initial, the states, if the initial to final state, they are the same. So at time t, this map UT, they are the same. So now what we are saying with our theorem is that this is actually sufficient to show that for every stage, this map will be the same. Okay. So this would be obviously would be trivial if the Hamiltonian would be the same, but the non-triviality comes from the fact that the Hamiltonian are different. Obviously, this happens in other inverse problems, but in here it has a, I would say more like, I don't know if a simple way of understanding, simple way of seeing it. Okay. So now let's talk about the orange street. So how we found, how we solve this problem, what we did for that. Okay, so what we did for that is to establish an inverse problem. So we established the initial to final inverse problem. So the inverse problem will be, it will be simple, right? It will be, the goal of the inverse problem will be to determine the potential V, which is the only, let's say, open part of our Hamiltonian, from the initial to final state map UT. That will be the first part, right? Determination. And the second part of the map will be, is it possible to compute the potential, the electric potential V from the UT? Those are the typical questions, right? In this inverse problem. Well, there are others like stability and so on, but in principle, they are, let's say that these are the most basic ones, right? So in that sense, we have, again, our theorem with Alberto was assume that V1 and V2 have super exponential decay for dimension greater or equal than 2. And then we are able to show that if this Hamiltonian has the same initial to final state map, the Hamiltonians are the same. All right, so the V1 is equal to the V2. That's the result, the uniqueness result. Obviously, this theorem has as a corollary the previous theorem, right? So now that you know that the Hamiltonians are equal, I mean, the evolution might have to be the same, okay? So here I say that the reconstruction of this inverse problem might have interesting applications. As you have seen, the motivation of this inverse problem was not the classical one, I mean, or at least the one that I have been seeing in many talks through the years since my PhD. So it was more about applications of the Caro problems. It's for the theoretical method for electrical impedance tomography. I mean, many other applications, right? In here, the application, I mean, the motivation of the problem was another one. Was trying to understand something that is happening, it's going on, and we wanted to put some foundational theoretical framework, right? To understand, to say, all right, there's not any more surprise about what data scientists are doing. However, I feel that reconstruction might have some interesting applications. I'm not sure about that, but it might happen. But why this would happen? So imagine that you have like a number of initial states and final state that you want to produce all at the same time. So now assume that this initial and final state that you want to produce from initial state to final state, you want to produce them all at the same time, and they are possible. This is important, right? That they are realizable. That means that there will be an initial to final state map that takes every initial states of those that are given to the final states that are given as well. So the reconstruction would tell you how to produce the Hamiltonian that could make this thing happen all at the same time. It's not like in controllability where you have one thing and it had to end up happening in two other things. No, this will be more. It will be like you will have many initial states, you will have many final states given. If they are realizable, let's say, then reconstruction would give you a recipe of producing that thing for many samples at the same time. Okay, so I don't know if that's it might be interesting. It's a different perspective of the previous way that I have thought about the inverse problems. In any case, about the inverse problems for the dynamical Schrödinger equation, there have been like many authors working on that, and actually you can see a list of them: Aisha, Belasue, Shuyi, Dos Santos Ferreira, Mesri. I'm sure that I'm forgetting their some. And also there are some other people that have been working with time-dependent Hamiltonian, Aisha, Shuyi, Eskin, Yang, Scorsi, Tetlow. I'm sure that there will be more. The way that I have seen in their paper is slightly different because they don't start with the initial to final state map. They work more on the usual Dirichlet-Neumann map. And obviously because the motivation was was different. All right. So now let's go to the map, to the orange tree. That's the way we solve the inverse problem. And let's start by the way I learned to go through in the inverse Calderon problem, right? So in the inverse Calderon problem, the first thing you do is just you prove your Alessandrini identity, right? So now let's prove the first identity. That would be an Alessandrini type identity in this situation. So let me call here sigma. It will be a notation to say to think of the whole slab, like the interval of time 0 to t and Rn. Okay, that's where all the physics for us is happening as a whole space. So now we are given the potentials V1 and V2. In here, obviously, you don't need to have the super exponential decay. This is basically the way you solve the solutions. This is the way that you will be type of the assumptions that you need for the potential. So now the story of this formula will tell you that it's relating the difference of the initial to final state mass for the two Hamiltonian related to the relation of the potential one of the first Hamiltonian and potential of the second Hamiltonian. And there will be a product of solution, the typical one in the, let's say, for the Calderon problem. And now the only thing is that the U1, it will be solution for the initial value problem. So this F that you see here is the initial state. And the other V2 will be the final value. The V2 will be the solution for the final value problem. It will say the same equation, just with the V2 conjugated, and G as the final state. I mean, this is actually my experience with inverse problem is that this is like a rather general structure that in here what you will have is a product of things, and one it will be for, let's say, for a solution, and the other will be for the, let's say, the adjoint. So in here it goes for the initial and then to the final. So just for fun, let's make a proof. How simple is this? So the proof of the identity, it goes as follows, right? So it will, you have the difference of the potential. Now you use the solutions for U1, so that V1 times U1, it will be just this free Hamiltonian U1. Then you keep the V2, and the same you do with V2, right? And now you have this integral that have no boundaries in space and only have boundary in time, right? There is the boundary at 0 and the boundary at time 0. And now you do the integration by part. You have to justify this part, but I mean, once you justify this is okay. You do your integration by part, and it's basically, this is just a derivative in time. There is only one derivative, so what you will be in that seeing is just the initial and the final time of the product of the two, right? So now this is something you keep like that. You keep this identity, and now you use a third solution. So the third solution, it will be now again a solution for the initial value problem with the initial state F. So the initial state will be exactly the same as the U1, right? But now you see the evolution in terms of the second potential, right? And now, if you do this exact computation in here, you end up seeing that U2 times T, V2 times T conjugate minus U20, V20 conjugate is equal to 0. Why is this? You just need to reverse this identity in here and just replace 1 by 2. If you replace 1 by 2, you will have here V2 minus V2, and it's obviously 0, right? So this is what you have. Okay, now that you have that this is 0, the only thing you do is you just add this quantity in here because it's 0. And now this part and this part, they goes away. You subtract because they have the same initial data, initial state. And then the only thing you see is the difference of the final states with this final state, right? So now you rewrite everything in terms of the initial to final state map, and then the thing is proved, right? Okay, so there is nothing. So this is the final state G, and this is the difference of the two initial to final state map applied to the vector F. So there is nothing very deep here. Okay, so now, as always, in this type of situations where you have this like integral formula, what you need to do is just to prove some orthogonality relation, right? So now you are given two potential, now you assume that the initial to final state maps, they are equal, okay? So now, because of the previous relation, you have this orthogonality relation. This orthogonality relation holds now for every U1, V2 physical solution. Let me say something about what it means here, solution, physical solution of this type of equations, right? It was what we have earlier. So why I'm calling here physical solution? I'm saying physical solution, those are the solutions that are in the Hilbert space at every time t, right? So that they are in L2 over n at every time t. So those were the solutions that I mentioned at the beginning. I said, like, if you put an initial state in L2, they will stay in L2. Those are the physical solutions. That's what I mean, I don't know much about physics, but that will always heard about physicists talking about that, is that those are the solutions that are in the Hilbert space. So here the Hilbert space is L2, so those are in here called physical solutions. Okay, so now what we have to do is just to prove the density of the product of U1 and V2. And once we prove this in some specific topology, we are done, right? Then we are able to say that V1 is equal to V2. And obviously, for all of you that know the Calderon problem much better than I do, this is the similar situation to the Calderon problem. All right, so there is nothing really new here. Just a little bit, just a few things, because you are in the whole space and so on and so forth. There are some subtle things, but let's forget them about. Let's forget them about for a moment. So now let's simplify the problem. So in order to simplify the problem, what I'm going to do is I'm going to take a function f that is a L1 in R cross Rn. So that would be something that depends on time and variable x, but that is in L1, okay? So I will forget about that. And then I will assume that, or I will ask myself, what happens if I have that f times this product is equal to 0 for every physical solution that I have in R cross Rn? Can I ensure that f is equal to 0? So that would be the first question, right? I remember when I learned about the Calderon problem, they did in a different way, like saying like it's the linear, right? But I like much better this way, right? It's like, this is a simplification of the problem. Let's make our life simple. Let's do this with in that case was the product of harmonic functions. Here is the product of this type of solutions, right? So, okay, let's see that this is actually a pretty simple fact. So actually, you take any type of physical solution there, U and V, they are just evolution of since there are no potential, it's the evolution of the free Schrodinger equation, right? So those are this type of things. This type of functions, once you write them in terms of Fourier transform and so on and so forth, you see that they are just superpositions, or they are a superposition of waves of this type, right? Of elements of this type. They are just things that are actually unimodular. This is important here. They are just unimodular things. They are temperate. They have temperate growth, right? And yeah. So now, because of the superposition, you can immediately simplify the problem. Let me avoid the reason why, but you can just simplify to think the problem of this product of like a superposition of solution is basically the same as saying that you have that the f multiplied by these exponentials are equal to 0 for every kappa and every eta, right? In that way. And if you see, I mean, you just need to rewrite that, I mean, and you see that this equality to 0 is basically nothing that's saying that the Fourier transform of f in space and time, the Fourier transform of that, evaluated on those points, is equal to 0 for every kappa and eta. Now the point would be as follows, right? Like it would be like, say, like, if those points, kappa and eta, that are like that, they produce enough, let's say, frequencies in time and frequencies in space, that would be done, right? It could be then the Fourier transform will be 0 and the function f will be 0. Actually, that's what we are going to see. We are going to see that there are enough kappas and eta there producing enough place where the Fourier transform of f vanishes. For that, we will take like a very simple we will take a very simple situation. We assume that the Fourier transform is 0 for this situation. That was exactly the same situation that we have in the previous slides. And now we are going to take a tau and psi. Those will be the dual variables of time and space, right? And now I will consider tau and psi so that the psi is different to 0. So now we will choose kappa and eta in these situations, and we will be able to say that the Fourier transform of tau and c is equal to 0. Okay? The fact that from here we will obtain the psi is trivial because you will have the difference of these two guys. So this part, it will vanish, and the only thing you will be remaining is this thing that is 1/2 of psi plus 1/2 of psi. This is just psi, right? So that's what you get there. And now for the product, it is a slightly more involved, but you will see that this is simple because what you have here is the same with signs are changed. So you have to do the square. And now the only thing you will see is at the end of these two guys that are the different, the only thing that you will be seeing is when you do twice the first plus the last one, right? And you do the difference, and this is exactly the quantity that is given by tau. So it's a very simple situation, right? So now for every tau and psi, so that the psi is different of 0, you already know that the Fourier transform is 0. Obviously, this you could have done for tau and c 0, 0. You could have just taken the kappa and eta 0 and the same obtain that the Fourier transform of f is 0. So consequently, the Fourier transform of f vanishes in a very large set, right? So it vanishes actually in all this where the psi is different of 0. Now, since the f that I have chosen was like L1, the Fourier transform was continuous, then I could conclude that actually the whole Fourier transform vanishes. And then by the inversion of the Fourier transform, I knew, but by the injectivity of the Fourier transform, I knew that I know that the f is 0. Okay, so that's actually a very simple way of showing that what Calderon did in this situation is actually simpler, or as simple. Why I say simpler? I say simpler because one nice thing is that Calderon need to use very exponential growing solution. In here, we haven't used solutions that are exponentially growing. They are actually have temporal growth. Actually, what we have been doing is actually for physical solutions that there are superposition of this unimodular. This has a slightly different, which is subtle and has some advantages at some points. Anyway, so this was just a simple observation. So now, how do we solve the problem? So let's get back to the full problem. So now we get back to the full problem. We get to this orthogonality relation where we have this product of solutions times the difference of the potential integrated, and they have to be 0, right? So and they are solutions for this equation. How do we proceed now? I mean, the simplest way to proceed, in my opinion, would be the following. Would be, okay, let's do U1 and U2, let's take it as a solution for the Fourier Schrödinger equation, and let's take a perturbation, right? So let's make a simple perturbation. Yeah, that would be great, right? I mean, that would solve the whole problem. And actually, it looks like similar to what happened in the Calderon problem. The point is that, well, this is not pretty correct, right? Because what you need at the end, and this is something that we learned from the Calderon problem, is that on the strategy of Sylvester and Ullmann, what we need is actually to see that these remainder terms are negligible with respect to the leading order terms, right? So we need to like introduce some type of parameter or something that make the remainder things like vanishes, right? So how do we do that? How can we do that? Okay, so how can we do that? So that we do using non-temporal exponential solutions. Now we will take another solution for the Fourier Schrödinger equation, which is now one that has exponential growing, that grows exponentially. So this type of solution is basically as earlier, but earlier there was there was an I, and here probably there was a minus. But now it's not anymore like that. This has now like a complex part, but it has an exponential, pure real exponential with a pure phase. Why are we using this type of solutions? So this type of solution is something that, I mean, this is something that we have learned through unique continuation, through the Calderon problem, along the years, right? So what does this type of exponential does? What are the ingredients they are bringing? They are bringing something in. They are very bad because they are exponential growing, but they are bringing something. What is what they bring to the problem? So they bring an exponential scale that is good enough to ensure that the correction terms will be negligible with respect to the leading terms, right? That's what you want. And that's why, this is why the real part of exponentials need to be there, or at least in our situation now, need to be there. So what would be the type of solutions we are constructing? So in general, they have a bit more complicated form, but I have chosen here to write down for the specific case where the parameter nu, is something that is nu, the modulus of nu, in the direction en, so that I can split the variables, right? To show you in a very simple way the solution. So now my type of solution, here it should be V2, right? So U1, V2. Sorry, this is a misprint. So it had to be in time. Then the x prime is for the n's, the n minus 1 first variable, and the x1 is the last variable, right? So now what we have is that the exponential will only depend on the final variable. The exponential that is non-temperate, it will be the final. And now this will be multiplied by two things. That it was something similar to what we had earlier, right? We had earlier free Schrodinger equation, solution for the free Schrodinger equation plus a perturbation. But now the free Schrodinger equation is not anymore in the same variables. It's not in the full variables. It will be only in the x prime variable, right? So in the x prime variables, you will be seeing the subset solution as we have earlier, but in the whole space, it's not anymore, right? It will be the product of the two. And this is the type of solution we are using in our work with Alberto. So what is the intuition? Why I said there, especially, I mean, I know for the experienced people, this is something that they know. For the younger people, I'm not sure that they are so aware of this. Why these exponentials are so useful for making the correction negligible. Let's see how this goes. So now you take the phase of the exponential that I have earlier. I will call it as a phi. Now it will be phi. This will be a complex function, okay? Depending on a parameter nu. Now I do my conjugate. This time I will do my conjugate of the free Hamiltonian, right? I partial of t plus Laplacian. And I do the typical conjugation. And in this situation with this type of function, you have the conjugation, it will be the free Hamiltonian plus something else. Okay? This something else, it's something that is a drift term going in the direction given by the vector nu, right? Okay, so now I will do the simple thing that the simplest possible thing that I can do to this operator, which is doing Planck-Charel theorem. If I do Planck-Charel theorem, what I will be seeing is basically the symbol of this operator, right? And the symbol of this operator will have a real part, which is given by this part, and there will be an imaginary part that is given by that. So now, since this is a symbol, I will have I have a L2 nor there. The symbol, what I will be seeing in the Fourier side will be the whole modulus. So that means that actually the real part of the operator and the imaginary part of the operator, the symbol, they will separate and will give this simple identity, just like a regular separation, because one is the real part and is the other imaginary part. So they don't interfere. It doesn't interfere with this. Okay, that's the whole thing. Now, if you remember for Poincare inequalities, if the W that you have has some kind of support condition in the direction of nu, support condition in the direction of nu, you are able to bound the L2 nor by the gradient in that direction. And you will control in that direction with the modulus. So you will have a gain in the whole modulus because the direction is given with the modulus. Okay? All right. So that's the philosophy. Okay? So in principle, the exponential scale has introduced something new that it wasn't present there earlier. Is the fact that you will be able to somehow control the L2 nor with a growth in the parameter nu by the full operator. This is something that it wasn't there before. This happens whenever you have the support condition, okay? So this, I'm saying here, this yields a gain in the L2 node with respect to the parameter node. This is obviously just an intuition, right? This computation is nothing about the proof of how you construct the solution that I mentioned earlier, but it's under the intuition. Why it's not like a proof? Basically, because we need to construct solution in the whole space, and they have to they cannot be supported or anything. So you have to do more work, right? For doing this. But anyway, what is the real reason behind this game? What is the underlying reason? At least the way that I see it, is that actually the conjugation of this operator is a perturbation of the operator that you have from the beginning with a symbol that has an imaginary part that grows. So the fact that these and these are, like, say, orthogonal in a way, this is where the reason is, right? It's the imaginary part. And that is given by the exponential, the real exponential. If you get back to your computations backward, you will see that happened because you have a real exponential. Okay. All right. So I continue. Then what are the challenges then of the problem? The challenges are in several places. And I don't want to discuss them. I want only to give like a big overview of the problem and the motivation. So the first of the challenge was the construction of the solution, especially the correction term, right? So for that, we need to prove new inequalities for the corresponding Fourier multipliers so that the terms could be corrected. The funny thing is that the Fourier multiplier, it was a slightly different to the one in the Calderon problem. If you are used to the one in Calderon problem, what you are basically doing, the critical surface in order to do this multiplier is it's supported, the critical surface is actually a sphere of codimension 2, right? Now the situation is slightly different. Now it's a surface of codimension 2, but in this time it's not a sphere, it's a paraboloid, okay? So this paraboloid, it has an infinite paraboloid, and you have to deal with it in a parabolic way. So actually it's funny because we are still working on this problem for doing different things with potential with the LP integrability properties, and there is where you see that the paraboloid is playing like a completely different role because you have all these Strickland estimates and so on. While in this situation, there is the paraboloid, but basically you look at that in an elliptic way. So you cut in an elliptic way. Anyway, so that's one of the trick here. I mean, the challenges here, I would say, is the construction of the CGO solutions of the proof of the new term. And then there is the exponential growing solutions that are put in there that I said that we were constructing that. They are now they are growing exponentially in some directions. Actually, that's the way we have used to make the corrections. They are not anymore physical. So the orthogonality relation has to be extended. Okay. And it has to be extended actually for the type of solutions we have. This is something that is in the literature, and it has been done in several papers, Novikov, Kenny, Ullman, Bassi, and so there are other people that have also faced this. The point is that the situation for us is slightly different, and you cannot basically refer to the same strategy, but maybe the spirit is basically the same, right? That the spirit would say like you have to extend it, and then there would be a density property. But in our case, since we are in the full space, it's not that clear with the topology where the density is going on. So I mean, that's the way we have gone through anyway. It has happened earlier in the literature. Actually, I have to mention here, because we mentioned in the paper, and also I don't know, maybe someone of you that knows the things that are underneath, you probably are already thinking like, why you roll like a super exponential decay if for these papers that I'm mentioning here, they don't assume that they are super exponentially decaying, that they assume less, they assume something that is exponentially decay or small exponentially decay. So yeah, we haven't gone through those like possibilities. So we wanted to keep just in the first step. So that's the way. And actually, my PhD student is actually thinking now about this strategy, how to remove this super exponential decay. Anyway, what is the take-home message that I would take from this talk to my place. So the first one, it would be like that there is a way of understanding computational scientists when they say that when you want to predict, you can forget about physics and just think of your data, or saying that if you have enough data, you can just forget about the physics and still making predictions. Right? So at least we have seen in here that at least under the conditions that the potential is super exponentially decaying, it could be true. I mean, I don't know how they would do, but there is not surprise anymore. And I'm sure that neither for any of you. But this has brought an interesting new aspect, at least from my point of view, of the application of inverse problems. Because now these inverse problems that we have been doing, they are not needed only for the theoretical framework for applications. It's actually a theoretical framework for things that are happening in the type of way that we have with this analysis, the data science, big amount of data, and so on. This is a way of giving a theoretical foundation of the data-driven prediction in general. So in this, I want to say that inverse problem is not only has application, not only from the classical point of view of this practical application, but also providing a theoretical foundation. Okay, and just as a comment is that the dynamical Schrödinger equation has some funny differences that are different with respect to the Calderon problem that we have been analyzing for now more than 40 years. Okay, so Katya, thank you for your attention, for the attention of the audience, and if you have questions or comments, I'll be happy to answer.
Thank you very much, Pedro, for the very interesting talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please? Okay, Pedro, I have a small question. I mean, you mentioned that you are working on with potential NLP spaces.
Yes.
Are you expect to prove a result in some Ln/2 space, or what is the goal?
That's a very nice question, Katya. I love it, the question. Okay, so let's do the following. So there is now I go to the problem. Yeah. So there is, if you want to put this in a LP, let's say here LP LQ in general, you have to first set up the problem. For setting up the problem, there is a range of functions where this can be put. This is something that there is in a paper. There might be in some other places, but there is at least in a paper of Ionesco and Koenig where this is used using the Stricker estimates. Stricker estimates in the full range. So for those who don't know, Stricker estimates are inequalities where the Lebesgue spaces, the solutions U, is bounded in some mixed LP spaces by the initial state in L2. Okay, so therefore there were for a long time there was Stricker estimate, but it was already missing the endpoint of the inequality, right? So this endpoint was proved in '98 by Kiel and Tao, and it's rather nice proof, right? So now, in the problem that we are working with Alberto, in order to generalize this situation, we are able to put V in a place where the Stricker inequalities work, but without the endpoint. Okay, so the reason for that is that when you prove the corresponding, let's say, Fourier multiplier estimate that you have for constructing the remainder term, it will work, in principle, it should work in exactly the same spaces as the Stricker inequality. But so far, we have been only able to prove without the endpoint. So the corresponding endpoint of Kiel and Tao, we don't know how to do it. And I think for a while, this will be, I mean, I don't think we will work on that. But for now, we are able to somehow, we are working on this, and we have already proved the inequalities, but the whole project is not finished yet. But we are able to somehow not reach the way that you are saying, where it's ln/2 here. We are not reaching that point. We are reaching something different, because that would correspond to the endpoint of Kiel and Tao, and that inequality we're not able to do it.
I see. Thank you very much. It's very interesting and very difficult problem. Thank you very much. Are there any other questions or comments, please?
Yes, please.
Please.
Yeah, so hello, Pedro.
Hello.
Concerning the point here, so what is the point in for Schrödinger operator? Schrödinger equations.
Sorry, I don't think I understood.
Concerning the endpoint, so what is
Yes.
here the end point?
So you mean for the endpoint where in the
For the
top or in the
potentials.
thing that we have been discussing?
Well, yes, for where you have been discussing concerning the potentials.
So if I remember correctly, it would be L infinity in time, ln/2 in space. And then you have to assume some kind of a smalling assumption because there is a way, I mean, this assumption is needed for the direct problem itself. And this assumption is written in the paper of UNESCO and Kenny that I told you.
So here use some kind of Bosov inequalities or LP inequalities.
Yeah, so in order to obtain those, you will be needing to have a Stricker inequality. So if you remember what I have mentioned earlier, I have mentioned that you need to, in this type of problems, the multiplier will have a critical surface that, as I mentioned earlier, it would be like a paraboloid of codimension 2. For having the paraboloid of codimension 2, you need to see how the Fourier transform is basically restricting or concentrating, more than restricting, how much is concentrating around the paraboloid, which is the critical surface. That's always what happens when you need to invert, right? So how much the Fourier transform is concentrating. This concentration is exactly quantified in a way by the Stricker's inequality. I haven't seen the way of applying them directly to our problem, but the philosophy, yes, at least for the non-endpoint. The endpoint is a different strategy, it's a different story, and it's hard to explain now why it's so different to the kill and tau, or at least the way that I understand now. But if we have more time in the future and we finish the paper with Alberto, I will show you. But yes, so eventually the thing is about the concentration of the Fourier transform. So think of the Calderon problem. The sphere, the singular surface was a sphere of codimension 2, and actually those were the indexes that were related to the restriction on the sphere of codimension 2, right? So one dimension less. So let's say that Stricker inequalities will play the role of Stein-Thomas earlier, but now with a difference that is not so clear how to apply them immediately. But I mean, similar situation.
Yeah, thank you. Thank you so much.
Thank you for the question.
Thank you very much. Are there any other questions or comments, please?
Yes, a quick question. So you've detailed an approach to kind of a uniqueness result, but does this lead to a reconstruction algorithm, something effective?
Not really, that I don't know. I mean, I don't know. I mean, the honest answer at this moment is that no. I don't know how we proceed to the let's say to a reconstruction algorithm. And one of the things it would be that I haven't thought much about the problem, but one of the difficulties that I would say that would make this problem interesting, not only from the point of view of application, but from the mathematical point of view, that there are some challenges, is the fact that the integral formula, where the integral formula where I have related the potential with the data, is not something that you can use for the type of solutions that we have for complex geometrical optic solution, because they are not physical anymore. So this is something that you will have to see somehow in the limit, because as I said, you have to extend these two solutions that are the one that I have written earlier, that they are not physical anymore. So in principle, I would see that there is a challenge already in the way that you will give a reconstruction algorithm for this. On the other hand, I believe that it could be useful for other applications, but effective in terms of computations, I don't know.
Okay, thank you.
Thank you for your question.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments? Okay, if not, thank you very much, Pedro, for the very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you. Thank you.
Thank you very much for everything, for your attention. And thanks.